alunos da Agência Nacional do Petróleo, PRH 17, Engenharia Ambiental na Indústria de Petróleo, Gás Natural e Biocombustíveis, e o Programa de Engenharia Ambiental da Escola Politécnica e Escola de Química da UFRJ. Hoje nós temos a grande presença do professor Heriberto Cabezas, que vai apresentar a palestra em inglês. Então, agora em diante, eu vou me referir ao professor em inglês, mas gostaria de lembrar que, ao longo da palestra, as perguntas poderão ser escritas no chat, se identificando, e elas serão repassadas para a sala onde nós estamos transmitindo. Good afternoon, Professor Heriberto Cabezas. Thank you very much for being with us today. And Professor Heriberto Cabezas will, his talk will be on path to global sustainability. He's a professor at the Research Institute of Applied Earth Science and the University of Miskolc in Hungary. He retired as a senior science advisor, Land and Material Management Division of the US EPA in April 2019. He's past chair of Engineers Forum on Sustainability, representing all of the major professional engineering societies. His awards include 1998 US EPA Science Achievement Award in Engineering, 2007 Distinguished Alumni Achievement Award from the New Jersey Institute of Technology, 2011 Research Excellence Award in Sustainable Engineering from the AICHE, and 2013 Lawrence K. Cecil Award from the same institution. Dr. Cabezas holds a PhD and an MS from the University of Florida and a BS with magna cum laude from the New Jersey Institute of Technology, all in chemical engineering. He served as U.S. Embassy Science Fellow in Zagreb, Croatia in 2014. He's a fellow of the American Institute of Chemical Engineering, a member of the American Association for the Advancement of Science, and a board-certified member of the American Academy of Environmental Engineers and Scientists. Dr. Cabezas is the co-founder of the Transatlantic Research and Development Interchange on Sustainability, TARDIS, workshop series, held biannually since 2003. He co-leads the International Work Group on Global Sustainability. His publication includes over 100 peer-reviewed articles and chapters, 2 edited books, a US patent for electrochromatography, and 2 major software. One I use a lot is WAR, from EPA. He's one of the co-authors. His current research interests focus on the design of sustainable chemical process and the supply chain, the development of models and policies for global sustainability, and the study of pandemics as complex systems. Dr. Cabezas is a decorated US Navy veteran of the Vietnam conflict. Dr. Cabezas, thank you very much once more, and the floor is yours.
My pleasure. Okay, 1 second to start the slide. Okay. And let me know, can you see my first slide?
Perfectly, yes.
Perfectly. Okay. My pleasure to be here today. My name is Heriberto Cabezas again. And I took pictures of the 2 aspects of my life. You can probably guess which is the European city and which is the American cities. My family and I live in Cincinnati, Ohio, about a little over half the year, and the other half I am in Miskolc, Hungary. And so I travel remotely and I work remotely quite a bit. Collaborators in the work I am going to present include people from 3 different institutions, Urmila de Wecker, and Apurva Nisal, from the Wishwa Mitra Research Institute at the University of Illinois. Wishwa Mitra is a private research institute. Yogendra Shastri and Niraj Hanumante from the Indian Institute of Technology in India, and Natalia Cano Londoño from the National University of Colombia. And I would say that each one of us has different set of skills, so we contribute more or less equally. It's hard to tell when you're working with people exactly who said what when. I have quite a bit that I would like to say, and I'll try to get us through all of this without abusing your time. I want to talk a little bit about global sustainability, the sustainable systems hypothesis, which is sort of an organizing principle, the generalized global sustainability model that we are working on, and talk a little bit about the model in detail and talk about some scenarios. Then I have to introduce you to a little bit of information theory. And lastly, I'll show you how we use all of these things in trying to design policies for sustainability. Excuse me. So first, global sustainability concepts. Sustainability is a normative human concept. The planet has no problems getting rid of a species and making up a new one. We human beings are the ones who are not happy to just disappear. So sustainability is about maintaining conditions, physical, environmental, biological, economic, social conditions on Earth that make civilized human existence possible or feasible for as long as possible. Nothing lasts forever, but we want this to last as long as we can. Now, to put this in context, this is a plot of the human population over the span of recorded human history, which is about 4,000 to 5,000 years. And I don't think I need to elaborate the point. Look what has happened to the population over the last, say, about 500 years or so. It has skyrocketed. It's amazing how many people we suddenly have, and that's due to improvements in agriculture, health, and so on. If we look at the economy, it's even sharper. Again, this is a plot of real global world product, global equivalent of the gross domestic product over the span of recorded human history, which is about 4,000 years or so, 6,000 years. And again, notice that it's only in the last few hundred years that the world economy has really taken off. So the important part here is that there's a lot more people doing a lot more things as shown by the gross world domestic product, but the planet didn't get bigger. We still have one planet. So let me just go on and talk a little bit more about that aspect. This is a plot that I borrowed from a former colleague at the US EPA, Matt Houghton. And it's the world ecological footprint and the world biocapacity, plotted over the last 40 years or so. The ecological footprint is the land area that's needed to support the human population, the per capita basis. And the biocapacity is the amount of land that is actually available to support people on a per capita basis. Ideally, you would like to have more land available to support people than actually exists. Unfortunately, that's not the case. Before about 1977, yes, we did have a bit more land than we had the need for it. But after 1977, there was a crossover. Now, I don't know how many of you were alive in 1977, but I do remember 1977. And notice that the total ecological footprint on a per capita basis hasn't changed that much, but because we have more and more people, the biocapacity is shrinking, is decreasing. So essentially, we're using more planet than we actually have. So what are we trying to do here? Imagine a system that exists in some kind of a space. This is just conceptual, where there is ecosystem burden on humans on the system, ecosystem integrity, economic productivity, energy resources, human well-being, stability. More about this in a moment. But these are basic things that are needed for civilized human existence. And this change over time. So the system has some kind of a trajectory. So imagine that the world has a trajectory in this space. At any point in time, we exist in one of these points in the curve. But there is a limit, because to be sustainable, we're constrained to operate within certain limits, meaning if the economy goes up, the burden increases, or the energy being taken out of the environment changes, the human well-being goes up or down. So there are limits. What those limits are exactly is not important at this point. We just have to recognize that they exist. Okay. So we would like to steer the system, the trajectory of the system in that state, in that space. The problem is that we don't have a line, we have a fat curve. And the reason is that we have an awful lot of people, an awful lot of economic activity. So the margin that we have to maneuver is actually not that great. You know, if you try to steer the system, you bump into the walls very quickly. So this is not an easy problem. It's a solvable problem, but it's not an easy. Don't ever get the impression that we're just going to do this easily. So, sort of guide that we're thinking, we formulated the sustainable systems hypothesis, which says that there is about 6 things which are essential for civilized human existence. Let me change move the figures a little bit. Okay. There we are. The human burden on the ecosystem needs to be reasonable. It cannot be high. The ecosystem has to maintain its functional and trophic integrity. It has to work, the local and global ecosystem. The economy really needs to produce more value than it consumes. Otherwise, at some point you drain the value that exists in the environment, in the world. The quality of human existence has to be above some reasonable minimum. Exactly what that minimum is negotiable. There is a minimum. The use of energy resources from the environment has to be somewhere in the neighborhood of the environment's capacity to renew them. If you drain faster than it renews, eventually you run out. And the overall system has to maintain its order and self-organization over time. This is embodied in another hypothesis that we call the sustainable regimes hypothesis that we will talk about in a moment. So there's a couple of important things here. First of all, these are minimum requirements for civilized existence. There's about 6 of them. If you want to add one, yes, you can. Some of them may not be too important in some specific situations. There aren't 50 things that you need to worry about. There's 5, 6, 7, perhaps. It's a relatively modest number of things that are really important. That's probably the most critical thing to keep in mind. Now, the Generalized Global Sustainability Model, the acronym is GGSM. Everything seems to have an acronym these days. And we just look at previous global models, and we realize that many of them cannot be used to generate solutions. They're more interested in forecasting, looking at the future, which is important. More important, perhaps because I'm an engineer by training, I like to solve problems. Yes, you tell me things are difficult. I know that, but what are we going to do about it? What can we do about it? And this is what this model is focused on. So it encompasses quite a few things: food, carbon emissions, other emissions, biopower, etc. We'll look at that in a moment. Okay, but it's a solutions-oriented model, and it's a 12-cell aggregated model. This has been in progress for at least 15 years, if you look at the dates in some of these publications. It has a rudimentary social system. It has a macroeconomy, a price-setting macroeconomic model, and it's supposed to be a representation of an aggregated representation of how the world might work. So what are the consistent components? This is what the diagram looks like. There we are. And there are, let's walk through this. There are 3 plants, 1, 3. 3 are wild plants. They don't have, they're not private property. They don't have economic value. P1 is domesticated. There are 3 herbivores, H1, H2, and H3. H1 is a domesticated herbivore, H2 and H3 wild. And there are 2 carnivores, C1 and C2. There's a human population, HH. There's an industrial sector, an energy producer. There is a water reservoir. There is the capacity to recycle water. Inaccessible resource, the resource pool basically represents all the nutrients needed for plants to grow. To make a long story short, and the inaccessible resource pool is mass that is biologically inaccessible, at least on the short term. It slowly trickles back into the system, but takes much longer. Same thing with the inaccessible water reservoir. It's polluted water, basically, that's inaccessible. There is a fuel source that's not renewable, but the energy producer, EP, can produce energy from either the fuel source or from biopower. So there is a component. There is a rudiments of a legal system because the domesticated species P1 and H1 have economic value. P1 represents in a very aggregated manner agriculture. H1 represents in a very aggregated manner raising animals, ranching. And there is various cycling and recycling of flows. Some of the flows, the ones are influenced by humans, others are not. Humans, unfortunately, cannot control everything. Let's see, the industrial producer, the industrial sector, the energy producer, humans contribute to the inaccessible resource pool. There's an output that goes there, etc. And if you have a specific question as I'm going along, please stop me and I'll slow down or move back. Now, there is a mathematical model. I am not going to pretend that anyone is going to remember a bunch of differential equations shown to you for a minute or two. I just want to make sure that you understand that they exist. These are based on the ideas of Locke and Volterra from about 100 years ago. And they are basically mass balance equations. And they represent the growth and death of different species of P1, P2, and P3. In this case, the three plants, which we call primary producers. For the herbivores, they represent the growth, the change in the mass really of herbivore H1, H2, and H3. These are often consumed by people, and they're consumed by predators. And lastly, these are and M, by the way, is the mortality rate for this species. So since these are the simplest equations, let me just look a little bit about this in detail. Basically, this is the mass of predator C1. This is the birth rate, essentially the growth rate of one, which is proportional to how much prey it has. Okay. This is the inherent growth rate of a herbivore. And if there is enough people, that tends to slow down, and this is the mortality rate. So again, these particular expressions are in a paper that's under review with PLOS1. Now, the macroeconomic components. This is a sort of a diagram of how value flows in the system and how prices are set. And essentially, without overdoing it, the owners of the industrial sector, the owners of P1, the plant, that's agriculture, H1, which is the herbivore, estimate the demand for their product. They set a price. If the inventory clears at the end of the period, the price is right. If the inventory runs too quickly, the price is too low. If the inventory something remains in the inventory at the end of the period, the price was too high and people were not buying it. The flow of money generates a salary for humans. There is a representation for human beings in this system. And there's also taxes. There's a government sector which collects taxes. And it's an iterative process. The industry sets the primary wages for people. It's the dominant factor in determining wages. And again, the wages will go up and down depending on the income of the private firms, P1, H1, IS, and energy producer. I almost forgot that. Okay. This is sort of a diagram of how that algorithm operates. Now, with your permission, let me just point out that again, there are expressions that represent these quantities, the stock, the amount of product left in a particular compartment, whether that be P1, H1, the industrial sector, or the energy producer. There's a price, there are production targets, there are wages, etc., etc. And wages, by the way, notice that there is a minimum amount of wage. I mean, you do have to pay people something, otherwise they don't work. Questions, anyone at this point? Let me see if there's anything in the chat. Okay. Let me go on to the parameterization of the model. Essentially, you've got a model like this, and the question is, yeah, it looks nice. There are equations that look impressive, but does it represent reality? And that's where parameterization and validation comes in. So we went and collected, widely available public data. The human population, actual historical and model from 1960 to 2016, projections for the future from the United Nations. We looked at we borrow from the Gombo model. It's another global model to help us get a decent estimate of what P1 might be, what it be like. This is actually the aggregate amount of agricultural plants globally. Okay. Next, we look at herbivores, and the student that's working on this, Urbanizal, her research indicated that about 60% of the animals on the planet are domesticated. It seems a little high to me, but she swears this seems to be correct. And humans represent 36%. So there's lots of domesticated animals, apparently, lots of people, and not many wild animals left. We also look at historical greenhouse and NOx emissions, and how these emissions go by sector. We look at the world GDP, which is available from any number of sources, and we parameterized, fitted parameters, and then made some comparisons. Basically, the top graph is the global population, and the model projections is the red curve. Okay. United Nations median projection is the blue curve, and the two dotted lines at the upper and the lower bounds of the United Nations population projection. One doesn't expect any model to exactly mimic populations, but the trends are correct, as much as we can tell. The lower graph is the global population in thousands, and this is historical, not the United Nations model. And here the model output, which is the red curve, the historical data are again fairly closely parallel each other, although one would not expect an exact match for any number of reasons. I'd be happy to go into that later on. These are emissions, carbon dioxide emissions, according to the model, the red line, historical data, the blue dots, and reasonable correlation. The nitrous oxide emissions, the lower dot, data quality seems to be a little more variable, but at least the trend in the data and the models are consistent, as best as we can tell. If I look at the world gross domestic product, economic activity, the model output are the red line, the historical data is the blue line. Again, we get a reasonable correlation between the two. Second, if you look at the sector emissions, essentially who is producing what for carbon dioxide, according to the United Nations, about 40% of the carbon emissions come from electricity, 31% from transportation, 14% from industry. The aggregation of our model is not exactly the same, but for electricity, we were right on dot. And for industry, we were right on dot. And residential, transportation, and commercial are aggregated. But if I were to add up residential, transportation, and residential and commercial, according to the United Nations, I get 41%, which is approximately what we have from our model. So we get fairly decent correspondence with observations. Lastly, there's two scenarios from the model that we will talk about shortly. There is the scenario one, which is business as usual, the scenario two, where the human population is increasing, and the medium variance, which is the blue line. And we wanted to compare these scenarios with the United Nations. So the scenario one, where the global population is increasing, no, scenario one is normal. scenario 2 is global population is increasing according to the model, is still within the bounds of the United Nations upper and lower variance. So we would argue that it's a reasonable projection. And notice that at this point we're doing a projection. I use the word prediction because no one can really predict, we can only project. And let's see. So let's look at some projections from the model. And incidentally, I cannot see the chat. Let's see if I can. So I hope there aren't many questions. All right. So there's a couple of 4 scenarios that we'll go through quickly. I'm looking forward about 130 years or so. The business case, business as usual, the base case, population growth, consumption increase, and population growth and consumption increase at the same time. A heads up, number 4 is where the real trouble begins. Number 3 is where the trouble begins. Number 4 is where it's really worrisome. I apologize, there are too many things I need to show you and I don't have enough space. But I hope you can see that there are plots for the carnivores, the plants, the herbivores, the gross domestic product, and so on. So these are plots of the important compartments in the model, the important things, the human population as well. And the green line is scenario 1, business as usual, nothing changes, okay? Scenario 2, and business as usual is not quite business as usual, is the human population is not growing or growing very little, okay? So we are saying the future is going to be very much like the present. And that's the red line on top. And yeah, things change a little bit, nothing drastic. Scenario 2 is when the human population begins to increase, and notice that some of the biological compartments, the mass begins to drop. You know, for the herbivores H2 and H3, for the carnivores, and so on. The GDP increases because the more people, the more human activity. The human population increases. So the thing though is if you have more people, you tend to have lower per capita income, but the system is still functioning. If I now have scenario 3, consumption increase, jump fast. If I have scenario 3, population increase, and with consumption increase, notice that we now have problems because essentially the system starts to jump. Populations of some biological compartments, as you can see, reach near 0. Number 3 is consumption increase. Number 4 is consumption and population increase. Let's make sure this is clear. The blue line, that's usually, well, not always, sometimes on top, is just consumption increase. You have a stable human population, they're just using more resources from the environment. Okay, and that by itself causes problems. Notice that some of the biological compartments, the carnivores, start to disappear. Some of the herbivores disappear. The global GDP becomes kind of unstable. The human population is going up. When I have population growth with consumption increase, these things happen even sooner. Okay, that's sort of the yellowish or orange line that's often below the blue line. So the problem, the worst, most difficult problem is when you have population increase, rapid population increase with rapid consumption increase. Unfortunately, this is not too far from the situation that we see at the moment. Okay, so To make a long story short, if you have the planet, the human population is stable, then not many more people, the population is not growing fast. Consumption, per capita consumption is more or less stable, not changing a lot. Yeah, the system is fairly fine for a long time, okay? Let me go for a moment here. Notice that this is a projection until about 2040. So it's into the future, okay? If you are growing the population, then you start to have some difficulties because you're crowding out animals. Okay, so some species might decrease. If you have consumption increase, you're taking resources out of the environment. So not only is there a crowding factor, you also are taking resources which other living things in the environment need to subsist. If you have rapid population increase and rapid consumption increase, is what we call in at least in American English a double whammy, two hits at the same time, and that is the most difficult problem to manage. That's probably not far from the situation we have today. To discuss what you can do about it, I'm going to walk us through a little bit of information theory. All right, reality. There's something out there we call reality. And if you believe you are God, you have direct access to reality. If you're a human being like me, you don't. What you do is have observations of reality. You collect data. And unfortunately, the transfer from reality to your data is never 100%. You always miss something. There's something about reality that you don't capture by a data set. If I then go from observations to analysis to try to make some sense of this, you have one more transfer from data to principles, and that's where we, the observers, are. We look at the data, we infer something about it, and feature information is the amount of data that you and I as observers can obtain, the amount of information that you and I can obtain from observing data that was taken from experiments and observations of reality. Okay, reality, observations, the observer. Feature information is the information that's obtainable from the data. Now, this is just a definition. It was developed by the statistician Ronald Fisher about 100 years ago. And he was thinking in terms of fitting data. So it's the information obtainable from measurements of some variable S in an effort to obtain the value of some parameter zeta. If P is the probability density function for observing values of S in the present of zeta. In other words, you are measuring S, hoping to fit zeta. If the shape of the probability density function P is independent of the value of zeta, then you can remove zeta from the expression for the Fisher information pi, and you simply have an expression that's an integral over the values of S, the probability of observing a value of S, and the slope of the probability density function square. That's the expression we're going to use. Now, understand the following. If I'm making observations of S, which can be a function of multiple other variables, which can be functions of time, it doesn't matter. If P is a flat line, the slope, the probability density function is 0, and the information content is 0. If the shape of P is a shallow curve, like in the blue line at the top, I get a bit more information. And if the shape of the probability density function P is a sharp curve, like in the middle, the green line, I have lots of information. The reason this is important is because the red line, the flat line, is a disorderly system because all values of S are equally probable. The green line is an orderly system because only certain specific values of S are equally probable. The argument I'm making is that the Fisher information I is then a measure of order in the system. A disorderly system has zero Fisher information. A highly ordered system has a high value for Fisher information. If you compute Fisher information, and this is just for your information, by a series of transformations that eventually amount to taking the first time derivative of the observable variables, whatever variables you're looking at the system, the x's, the first and second derivative. We've been doing this for about 15 years. So this is nothing new. It's in the literature. If you Google me, you'll find any number of papers talking about this. Okay. This allows us to formulate the sustainable regime hypothesis, which says that Fisher information is a measure of dynamic order. Well-functioning ecosystems have to have order. A disorder biological system is probably dying or dead. Okay, so if you're looking for a system which is sustainable, then the Fisher information has to be stable over time, meaning constant or at least relatively constant, meaning the first derivative is near zero. And this is a fairly firm requirement for biological, economic, social, political, and all the systems that I know about. Okay, when they're functioning well, Fisher information is stable. If you have a steadily decreasing Fisher information, then you have loss of dynamic order, and the system is getting disorganized and ceasing to function. Not a good situation. You can have different stable regimes of the system, but the change between two regimes is often a sharp drop in dynamic order and the Fisher information. Again, we have seen this in multiple systems over time, including social, political, economic, and biological systems. This helps us to try to design solutions to the problems that we were discussing a little bit ago. So I'm going to do an illustration with a previous version of the generalized global sustainability model, because the development of the policies with the current version of the model is research in progress. So we say, all right, if you must have a stable Fisher information, we can then look for a system where we try to minimize the fluctuations in dynamic order. So we pick a base case for the Fisher information system that's stable and working well, like the base case we previously discussed, and that's ICE of C, the Fisher information for that system. ICE is the Fisher information for the system at this point that we're looking at. And we minimize this difference, the square of this difference to be exact. And we were able to find by this control scheme that we could create a stable system if we could manipulate the fee that's placed on the industrial sector for pollution, the fee that the government imposes for the owners of H1 to have their animals graze on public property plants, P2. We found out that we could change a little bit the parameter, the price of P1, okay, the relation of the price of P1 to the demand. We could also change the parameter relating to the price of H1 to demand. So this essentially is playing a little bit with the unit price, of the agricultural plant P1 and the domesticated herbivore H1. And we also needed to change zeta P1, not the zeta from Fisher information, please, which is the amount of plant required to produce a unit of industrial product from the industrial sector. This is an engineering technological question, and we also needed to manipulate the amount of biomass needed to produce a unit of biofuel. Again, this is a logical problem, it's an engineering problem. Important part here. Two of the things that needed to be changed are regulatory policy, or economic, or technological. And if we do all of these things, we found that the system can be kept stable for at least 200 years. Okay. Here I have the P1, H1, the carnivore, and the fishery information. And it does fluctuate a little bit around. When you have the control system, that's the green line. Notice that things don't go extinct. The system is on control. C1 goes extinct, E1 goes extinct, H1 goes extinct. The fishery information goes to zero, so the system is disorderly and dysfunctional. And the base case is the blue line in between. So to make a long story short, yeah, you can make it work, but you have to play with a number of things. So in summary, the generalized global sustainability model includes quite a few things. I forgot to mention, it has a seasonal variation in the growth of plants, a high and low season. One high growth and one low season is a year. That represents winter and summer. The results for population, gross domestic product, carbon dioxide emission, nitrous oxide, are consistent with observations. GGSM provides an avenue to craft social, economic, technological policies that may make sustainability possible if used in some kind of an optimal control process. The optimal control process is not meant to run the world, it's just meant to give us an idea of what to do. Essentially, we're looking for feasible pathways to sustainability. The scenario analysis provides a self-consistent possible futures, but it's not a prediction. We're not in the business of predicting the future. We do not have crystal balls. And one thing I should note, which I didn't dwell on, is water is globally available. There's more than enough water in the planet. This is usable fresh water, excuse me. The problem is that regionally, it's not. Some regions have too much water, some regions don't have enough. And I'd like to thank you very much for your attention. The second one is Hungarian. It means thank you very much. Hungarian is interesting. Last one is Spanish. Thanks a lot for your attention. I'll stop sharing, and I'll be happy to answer whatever questions that you might have. It was a lot of information. I'm sorry about, I did a court on all of you.
No, that's very interesting. I have one question from the audience, from Fernanda Mello, and she's wondering if the model accounts for circular economy. How would it change?
Yeah, there is a recycle. There are recycles, yes. Mm-hmm. There are recycles built into the model. The problem is there's so much detail in the model. It's difficult to compress it to about an hour. We haven't really explored that extensively, but we will. It's not difficult. implicitly it's there, but it's not done adequately. So to answer her question, no, we really have not done a good job on looking at circular economy, but we will.
We have another question from Jorge Victor Brigadão, and he's asking if the model could be modified to have some social inequality consideration. And if it is possible, if you have tried, or if you think it could work.
It could be done. At this point, the human population is an average, the mean field model. In physics, it's called a mean field. It's an average. So no, we have not segregated the human population into different sectors. We started to do that, something like that for water, where there are regions which are putting water and regions which are rich in water. A model like this, you have to make one change at a time. See what happens, and then you make another one. If you make more than one change at a time, you lose control of the process and you get pretty confused. And that's the voice of experience speaking. I have made many changes to a model and then I don't know what's going on. So I agree, it's important, but we haven't gotten there yet, but we will at some point. The same thing with circular economy.
The next question, it comes from me. I'm very curious about it. And you look at the global situation as a control system, and then I'm worried about it is a huge system in terms of dimensions and order, high order system, and with lots of time delays and inverse response and everything that makes controllers worry about getting what they want to get from the system. And then comes the question, the world trying to move so fast on CO2, as I would say that the objective function nowadays is mainly for CO2. And you change everything at the same time so that you think you are contributing to sustainability with a very strong action towards reducing CO2 emissions. So my question is, with such a complex system, and is the world going into the right direction, centering all its efforts on CO2 or the main?
No, that's not, no. The control objective is minimizing the fisher information, which includes everything. It includes all the biological compartments. No,
I don't mean your model. I mean the world.
The world itself.
Yes.
Oh.
Yes.
Oh, no.
I think it's
no. I agree with you.
Every variable can move everything, and then we are just moving to one direction.
No. I mean, look, reducing carbon emissions is something that needs to be done, but it's not the only thing. Okay, so I do worry that the world is narrowly focused on reducing carbon emissions, nothing else. And that's difficult. I'm not sure how that's going to work. We'll see. Because there are lots of other things going on. Species extinctions. It's something that worries me quite a bit because we don't the climate we understand reasonably well. There is other things going on that we don't understand nearly as well, like the loss of species. So what is that going to do? And I don't have a good answer. I don't think anybody does. So yeah, I wish there was a broader perspective, but even getting action on carbon emissions is very difficult. So at least we just want to prove that it's possible to move towards sustainability and have some pathways that should get you there so that the so that when you have to make real decisions, you have some guidance. You have some idea where to start, where to look. No, carbon emissions is not the only thing going on. There's many other things going on. This is true.
Maria Alice, she's in the room. I don't know if she was having some problem with her mic.
Okay.
Hi,
Oh, there you are.
Hi, Heriberto.
I'm inviting her to keep the debate warm.
Thanks for the invitation, Ophelia. It is very nice to see the model, how it can work. In fact, in Brazil, we are now having a lot of problems because of the low level of our water reservoir. So there's a problem from energy that is coming out. So we are not so sure what is going on in the next months. And what I would like to ask you is, because it's focus on CO2, on the emissions and the environmental, but this kind of problems can be also, as people asked about the social problems that I said, this kind of problems can be also predicted or added to your model?
Okay, water. The model now includes water. You know, but
the changes on the rains and this kind.
Yeah, yes, it's a fairly sophisticated model, including water consumption by industry and people and agriculture. Agriculture is the biggest one. Industry is small. Agriculture, people, and then industry.
And electricity.
For industry production.
Yeah.
Good. So no water, no electricity. So social unrest and things like this, which is a problem, we're not there yet. The human population has an agent-based model, which makes it possible to include things like this. But again, we have to do this a step at a time. We have used visual information to show the evolution of socio-political systems. We have papers on the subject out. If you remind me, I can send you copies. And yeah, the visual information drops when the country becomes socio-politically unstable. We have data on the whole world, basically. And we also have data for 3 major countries, France, Germany, and the United States, over the span of the 20th century. And it's very, very interesting. Whenever the country is running into trouble, it becomes disorderly and the visual information drops. You can actually see it coming. You can sometimes even predict which country is at risk and which country is not at risk. There is almost if I post socio-political upheavals, I know I'm straying away from the talk, versus visual information for countries. There is a very sharp divide. It's almost like a phase transition, like a melting. On the high visual information side, you have very few socio-political upheavals. On the low visual information side, you have lots of them. The transition is very, very, very sharp. You go from near nothing to a high number over a tiny change in visual information. It's a tipping point. So these things do exist. I mean, countries hang on and hang on and hang on, and at some point it explodes. So anyway, but at this point, we just wanted to see if it was even possible, in principle, to be sustainable, because that's not clear. And we think at least we have some reason to think that it is possible.
Heriberto, we have a question from Bruno Borges Mamede, and he comes to Latin America context, and he's asking if you can see an equality among production technologies for food production, and how would it impact the environment using different technologies for food production. He's mainly thinking of the nexus of food and
in an aggregate way, basically, if you can grow food with a bit less water and less capital, because water costs money, then you're more efficient, yes. But it's in an aggregate way. At this point, we're not in a position to compare two different ways of growing food. Again, this is at the global level, so there would be probably way too many differences to be included. But it's in there, but in an aggregate way.
Okay, and again from Bruno Borges, and he's asking what would be an alternative to the classical non-sustainable production agriculture, if the small properties, small producers, if it could be more sustainable, like moving the agribusiness to small production, if it would be beneficial to the global sustainability.
If it's more efficient, yes. The question is it more efficient?
Is the size of the big agribusiness against the small one, if the size of the production scale of one single producer, if that would help sustainability or not?
I don't know. Not from this model, I wouldn't know, because it's an
a lumped model, so it doesn't have.
As long as you produce enough food,
it doesn't.
Fed.
It doesn't account for.
It doesn't account for that. No.
Okay. Okay. I have one question. Just a minute. Sorry.
No.
My question is about the model taking the world as a stirred tank, a perfectly mixed tank. And it could still be working with several small tanks, like taking our model and fitting the parameters for each economy or each by GDP, for instance. Do you think that could work, and summing all the minimizing local fisher numbers, if it would be possible to treat the world and to have political?
You can. I mean, here's the thing: the world is close to mass, open to energy. Basically, we not too much mass comes in or out. So the natural boundary for sustainability studies is global.
Global, yes.
No, a local region within the planet, it has the issue that you have lots of things coming in and out, and you have to characterize those and know what those are. Now, if you were to break up the globe into a series of subsets,
yes,
connect them,
and then have some international market, carbon credits, water credits, and
you could that could be done. It would be a massive undertaking, though.
It could be a PhD thesis.
No. It would be several PhD theses. You know how you break up, because each subset would be a PhD thesis on its own. Then you have to connect them and so on. So yeah, it can be done. It would be mathematically complex, but it could be done. What we have done so far, we were just interested in being able to argue with some confidence, sustainability is possible. That was it. That's why I started this model when I was at the EPA. The initial diagram was drawn on my whiteboard in my office. Okay. And then it's continued. Then I began to collaborate with Surmila Wecker because I couldn't do that kind of work at the EPA anymore. So I just moved it to her, and now she's sort of been. Her and I are basically co-leads. You know, we've known each other for a long time, and others have been involved. So it's we added water, so we keep adding details. I know what you're saying. Yeah, so globally it may be possible to be sustainable, but how do you execute these actions at the global scale where it's possible to execute actions? So eventually I will probably need to have subset the world and connect them. We've done that for water.
Yeah,
Out of necessity.
Continents, and then
we did it for continents, for water, because water, you cannot move water, it's too cheap. And it's cheap because it's subsidized, by the way. Everybody subsidizes water across the globe, because if people don't have enough water, they revolt. And the last thing a government wants to see is a revolt because their people are thirsty. So subsidized water, but it's local. So, well, I mean, that's my effort to answer the question, which.
There is one question from Aristides, and he's asking if you could share the presentation.
Should be able to. I'll need to ask my co-authors just to make sure they're comfortable.
Okay, and your webinar will be on the internet. Is that the problem? Because we keep it.
No. If I was still at the EPA, it would be difficult. I'm a private citizen, so yeah, you can keep it on the internet. Okay.
Well, it's we could stay here for the entire day. I have many ideas with your models, and I hope we can absolutely collaborate. And Alice, do you have a final question of that?
No, I have only to thank Professor Heriberto to be here with us, to talk and to show these results are very interesting, and hoping that this collaboration could be better even more. Thank you very much.
You will. Thank you. Thank you.
Thank you, Heriberto. And I will switch to Portuguese. Eu agradeço a presença de todos e a apresentação ficará disponível no canal do YouTube. O professor consultará os seus coautores e poderá compartilhar a apresentação. Mas, a princípio, a apresentação está gravada e vocês terão acesso ao conteúdo no mesmo endereço em que ela está sendo transmitida agora. Okay, thank you very much, Heriberto.
Thank you. All right. Goodbye.
Alice, você pode ficar na